Hi, my name is Andreas Hinterreiter. I'm a PhD student at Johannes Kepler University Linz and have spent the last year in the Biomedical Image Analysis group at Imperial College London. In this video, I will present projective latent interventions, a method for understanding and fine-tuning classifiers based on manipulations of latent space embeddings. This is joint work with my PhD supervisor Mark Streit, who is full professor and head of the Visual Data Science group at JKU Linz, and Bernhard Kainz, who leads the Human in the Loop subgroup of biomedia at Imperial. Classification is one of the most important machine learning tasks, with a wide variety of real-world applications. In the medical sciences, the applications include drug target discovery and classification of imaging data. Just a couple of years ago, for example, colleagues from Biomedia published SonoNet, a network that can efficiently classify standard planes in ultrasound images. In the recent years, there has been a general increase in the demand for model explainability and interpretability. And of course, in medicine, this demand has been exceptionally high, given the consequences of choices based on machine learning algorithms and also the involvement of domain experts. Due to their high-dimensional latent spaces, neural network classifiers and their decision boundaries are notoriously hard to interpret. One method to get insights about the inner workings of such models is to visualize the latent space using low-dimensional embeddings. Many different projection and embedding techniques have been developed, both by the machine learning and the visualization communities. They range from the classics, PCA and multidimensional scaling, to more modern, nonlinear techniques such as ISOMAP, TSNE, which stands for T-distributed stochastic neighborhood embedding, or UMAP, which is short for Uniform Manifold Approximation. Here on the right you can see a visualization of the hidden activity of neural networks using TSNE. Such embeddings try to conserve some aspect of the high-dimensional latent space, such as variance or mutual distances. Especially TSNE and UMAP, which both try to conserve pairwise distances within a certain neighborhood of points, have been used with great success. But these techniques are separate modules that could only produce fixed embeddings. Here, with fixed, I mean that the embeddings are only mappings of exactly one high-dimensional point cloud to one low-dimensional point cloud. New and unknown data points typically cannot be added to existing embeddings, and gradients of the embedding function are impossible or difficult to determine. This makes these nonlinear embeddings only suitable for passive observation. With projective latent interventions, we try to change this paradigm from passive observation of the embedded latent space to active interventions. We approximate the embeddings of a trained classifier's latent space with a second neural network. This neural network-based embedding allows mapping of new data points and makes the calculation of gradients straightforward. The low-dimensional visualization is presented to the users, who can inject their domain knowledge into the process, for instance by moving clusters of points around in such a way that the embedding better matches their expectations. The manipulated embedding is then used to inform the subsequent retraining of the classifier, by adding an additional embedding loss to the original classification loss. Let me now explain the projective latent interventions workflow in a bit more detail. Let's assume that we have a classification model that is already trained. We set up a second neural network that takes high-dimensional vectors as input and outputs two-dimensional ones. We will train this network to perform an approximation of TSNE on our latent space data points. We calculate probabilities Pij of high-dimensional neighborhood of the points I and j. These probabilities are based on Gaussians and they are calculated once before the training of the embedding. In our implementation, we use a trick to avoid having to calculate the whole distance matrix. We then, just like it's done in traditional TSNE, calculate probabilities Qij of low-dimensional neighborhood. They are based on heavy-tailed t-distributions, and this is done batch-wise during training for the output of the embedding network. We optimize the network parameters by minimizing the Kullback-Leibler divergence between Pij and Qij. This whole approach is based on work by van der Maaten, but we completely re-implemented it in PyTorch and added a number of extensions. The resulting network is used to embed the latent space of the original classification network. The latent interventions then define a new desired embedding, and the classification network is retrained such that the new latent space has an embedding that is similar to the desired one. This is done by simply adding an additional mean square error loss term, with a weighting factor to control the relative importance of classification and embedding loss. We tested our approach on simple image classification tasks for the MNIST and Cypher-10 datasets. We tried two kinds of interventions: contractions of whole class clusters towards their center of mass, and translation of whole class clusters. In this image on the left, you can see the initial embedding with a focus on the clusters for the auto and truck examples of the Cypher-10 dataset. In our manipulated embedding, we artificially separated the two classes by shifting their clusters relative to each other. After retraining, the clusters indeed conserve the desired separation, and the class-specific performances for auto and truck were slightly increased. We then tested projective latent interventions on a challenging diagnostic viewplane classification task in fetal ultrasound screening. We selected a subset of about 4,800 train and 1,000 test ultrasound images, sampled from about 2,700 patient examinations. The selected images belonged to one of the following classes. 3 classes were cardiac views: 4-chamber, left ventricular outflow tract, and right ventricular outflow tract or 3-vessel view. The other 3 classes were non-cardiac views: abdominal, femur, and spine view. We trained a SonarNet to classify these views, stopping early for illustrative purposes. The embedding of the final layer outputs for the train data on the left shows that the 3 cardiac classes strongly overlap. We applied projective latent interventions to artificially separate the cardiac classes, as you can see in the manipulated embedding on the right. Afterwards, we continued the training of the network. Here on the left you can see the embedding of the final layer outputs after using pure classification loss. On the right is the embedding after continuing the training with our new loss function. The 3 cardiac classes are separated better, and many images in overlapping areas of the class clusters are classified correctly after the interventions. In this case, there was an absolute F1 score improvement of about 5% for the cardiac classes, while the performance for the non-cardiac classes remained the same. It should be noted here that the contour lines in these plots are not the decision boundaries, but simply density lines, but they still give a good impression of how severely the clusters for different classes overlap. From our experiments, we realized that the response of a classifier to projective latent interventions needs to be evaluated on 2 axes. On the one hand, we have to check how the classification accuracy changes with the additional loss. Does the model perform better or worse? Are there class-specific improvements? Or do the class-specific improvements hurt the other classes? On the other hand, we have to check if the resulting embedding is actually closer to the desired one, or if it has not changed much. For simple tasks, such as classification of MNIST images, we found that the network usually can easily incorporate the additional embedding information without much change in performance. For slightly more challenging tasks, we found changes in the resulting embedding are more often accompanied by changes in the performance. This co-evaluation of performance and embedding helps us to understand when the shape of an embedding is actually a good representation of the classification performance. One drawback of projective latent interventions is that even in simple cases, the embeddings themselves, even prior to the manipulations, can be tricky to interpret. This is especially true for people who are not used to working with TSNE or UMAP. So far, we also limited ourselves to simple interventions, contraction and translation of entire class clusters. It would be great to study instance-level manipulations in more detail. However, this comes with the additional challenge of how to let users explore and input these manipulations. In my group in Linz, we have developed interactive visualizations for similar tasks, so there is already some existing work on which such a user interface might be built. And with this outlook, I want to thank you for listening.